Thank you very much, Ellen, for the introduction. Yeah, I thought I wanted to talk about, I guess, the most common electrochemical or electrode material used in electrochemistry, that is platinum. And I am specifically interested in the surface chemistry of platinum. And also specifically interested in when the chemistry or when the interface between platinum and electrolyte, when we can describe that as a purely electrostatic system where everything is only governed by the charge that exists on the surface, and when not, and what then determines when we change potential, whether the surface actually charges electrostatically or whether chemistry takes place, and how should we then think about this system in terms of the classic double layer where we have one charge on the metal and a counter charge in the electrolyte. You will see not too much chemistry or catalysis in this talk. I mean, this turns out to be a complicated enough question with complicated enough answers that I can spend 1 hour easily talking about this and explaining to you all the mysteries that we have not solved yet and where I think we do not fully understand yet. But let me start from the beginning. So if platinum is the most used electrode material in the electrochemistry, then this would be the most measured, what we call CV, cyclic voltammogram in electrochemistry. This is a polycrystalline surface, platinum surface in sulfuric acid. And when we take when we do an experiment with platinum, this would always be one of the very first measurements we do. We take our platinum surface, we immerse it into the, in this case, sulfuric acid solution, and we run the potential between two limits, and then we should get a characteristic fingerprint of this interface. And if this characteristic fingerprint is the way we think it should be, or how it is documented in literature, then we know we can move on to the next step. We know that everything is in principle well-defined and clean, and we can move on. If you do this for a polycrystalline surface, you should measure something like this. And what you see here are basically 3 different regions. The first region here is what electrochemists refer to as the hydrogen region. And what happens here is we come, let's say, from a potential here of 0.4, and that's versus a certain reference electrode. I'll come back to that later. We see that there's a current flowing, and this current flowing is due to the reduction of protons, and they form adsorbed hydrogen on the platinum surface. And you see this happens in what looks to be 2 peaks. And then when we go back, so here we return the scan, we go positively, we see basically a mirror image of this signal, suggesting that this process is reversible. And we refer to this as the hydrogen region. If we then go a little bit positive, and we reach about 0.8 volts, we see that another reaction happens. So here water starts to oxidize, we make a platinum oxide. And as we come back, you see that there's a platinum reduction, and now you see this is not reversible. So apparently the way we make the oxide and the way we reduce it doesn't follow the same path. And I would argue this is not only kinetically irreversible, this is also structurally irreversible. That means that actually the platinum changes structure as we oxidize it, and as we reduce it, we do not end up with the same structure. This is not something I will go into details in the talk, but that's nevertheless something that is important to know. I'll show you a little bit that some similar things can happen when we go very negative. And then we have a region in between where there's no hydrogen formation, there's no oxide formation, and we like to think that this is the double layer window of platinum. So this is the region where the current that we measure should be purely charging current. So we charge the surface positively, and as we change the potential, this then leads to a current, and so the current that we measure here should be purely charging current. Now, I guess from the way I'm telling you this, you can already probably suspect that things are not that simple. And I would argue that mostly in this region, even this is not just charging current. It's much more complicated than that. Now, of course, we're surface scientists, so we know that if we really want to understand this at a more detailed level, we need to go to another surface. And here you see the same thing, but now on a platinum 111 single crystal And we changed electrolyte. We like perchlorates because perchlorates, we think, do not absorb very strongly. So we're not bothered by anion adsorption. And now you can see that if we limit the potential window, and that maybe that's something I should have mentioned, if we limit the potential window 0.05 and here 0.9, if we go more negative than here, obviously 0 is the equilibrium potential for hydrogen formation. So I would see a huge negative current here, which would be due to hydrogen evolution. Platinum is a very good catalyst for hydrogen evolution. So normally we limit ourselves to 0.05. If we ran the voltammogram in this potential window, you see that now everything is very symmetric. We have again hydrogen adsorption. Here we have what we believe is OH adsorption. I'm pretty sure it is, but you could argue whether there's direct evidence for the formation of OH. But you can now see that on platinum 111, this is reversible. You can also see that it happens in a peak with a funny shape. I will again not go into the detail. We refer to this as a butterfly. There's a lot of discussion about what causes exactly this shape. But one thing is that if we have exactly the shape, we also know that our surface is of good quality. And then we have something in between, which now I think is really a double layer region. I believe that here we can really argue that this is OH formation, this is hydrogen formation, and in between, there's good reasons to believe that this is really a double layer. You see that there's lines in this voltammogram, and those are the lines predicted by density functional theory calculations, where I expect OH adsorption at a certain potential. I say I have a certain coverage, and then I can calculate at which potential I would expect that coverage. And I can do that for hydrogen, I can do that for OH, and you can see that DFT predicts that at a certain potential I get a certain coverage of hydrogen, at a certain potential I get a certain coverage of OH, and you can see that they are far apart. That means also that in between, water should be stable. That's what DFT predicts. On platinum 111, water should be stable. And that's what we see. And you see that DFT prediction is not too bad. You can also see that it matters a lot whether you actually add water to the calculation or not. Clearly, because OH will have an interaction with interfacial water and will stabilize it. So that's what we observe. And one other thing that you can see is that these peaks here, if you integrate this current, you get the isotherm. Then you basically get the coverage of hydrogen as a function of potential. That means that if a peak is relatively broad, that means the isotherm is relatively broad. That means that there are repulsive interactions between the species adsorbing. This peak is broader than what you would expect on the basis of a Langmuir isotherm, so there must be repulsive interactions between the hydrogens adsorbing on platinum 111. And this is something that, and they're not very strong, they're still relatively weak, such that we can still use a mean field model to fit this. But we analyzed these interactions using DFT calculations. Here you see the adsorption energy of hydrogen as a function of coverage, and you see it gives a nice straight line. From the slope, you can sort of get an effective interaction between the hydrogens. And then we calculated this for a fully relaxed surface and for a surface where the platinums were frozen in their positions that they had before the hydrogen was adsorbing. And you can nicely see that the interactions are different. You can also see that there are jumps in comparison to the fully relaxed surface. And basically our conclusion was that at relatively low adsorption energies, basically the main, or the relatively low coverage, the main repulsive channel is through elastic distortions of the surface. So the fact that the surface relaxes in a different way in the absence and presence of hydrogen, that causes some kind of elastic repulsion. And that's the main interaction channel that we have between the hydrogens. Every time there is a jump here, that is when the average coordination of the hydrogen to neighboring platinum atoms changes. So here, the hydrogen always shares only one platinum atom. Here they start sharing more platinum atoms, and that leads to this jump. So here from this, we can already see there's two main reasons for the repulsion. One is the elastic distortion of the lattice, and the other is that as you increase the coverage, you start sharing platinum atoms, and that also leads to an additional interaction. The electrostatic interaction here is actually really relatively weak, and that's because the dipole that is generated by adsorbed hydrogen is quite small. Now, one thing is that the platinum 111 is a beautiful model surface, but it's not a very good model surface for realistic surfaces. They will always have steps and defects. And so we're interested in what happens when we start adding steps to this surface. Now you see the same voltammogram of platinum 111, but now in sodium hydroxide. And again, you see the peaks, hydrogen adsorption, OH adsorption. The shape of this peak has changed a little bit, but it's still in the same potential window. And now if we add step sites, and this is for a 15, 15, 14 surface, you can see that we have only one additional peak. And there's been a lot of discussion what the nature of this peak is. I'll try to shift that discussion short. I'll try to cut that short. But one very interesting observation of this sharp peak is that it is supposedly non-Nernstian. So this peak here, we ascribe to hydrogen adsorption on the step sites. You see another peak here. This signal was slightly miscut. So these are the 100 step sites. So the steps can have a different structure. And so depending on the structure, this peak appears at a different potential. But what is important, the peak is also sensitive to pH in a way that you would not expect. On the reversible hydrogen scale, in principle, if I change pH and per electron, I would transfer 1 proton, I would not expect the peak to shift on the pH scale, because the reversible hydrogen scale, in principle, should correct for that change in pH. So I would actually expect this to be a straight line. Or if I would plot this on the normal hydrogen scale, I would expect 60 millivolts per pH unit. But that's not what we see. What we see experimentally is a slope here of around 10 millivolts per pH unit. And if you're an electrochemist, you probably know that if you see something of 10 millivolts per pH unit, good luck trying to explain what is causing this. Yeah, we call that non-Nernstian. This does not behave according to what a normal Nernst equation would predict. Now, two things. My personal interpretation of this sharp peak, because you can also see now it's sharp, it's not broad anymore. And the other thing you can see, we see only one peak. We don't see separate hydrogen and OH adsorption. We see only one peak. So our interpretation is that this peak is not hydrogen adsorption. Actually, this peak is hydrogen being displaced by OH in one peak. That explains why we see only one peak, because it's basically replacement of one thing by the other. It can also explain, that's a little bit more of an evolved argumentation, explain why the peak is sharp, because actually we're replacing an adsorbate that is small by an adsorbate that is big, and that can lead to effectively attractive interactions. It does not explain why we have this pH dependence, but then I argue this pH dependence is only apparent because as we change pH, we typically also change cation concentration. It's very difficult to change pH without changing cation concentration. If we limit this experiment to a pH range where we don't need to add cations to change pH, actually there is no pH dependence. If we do this from pH 1 to 3, we see that the peak is always at the same potential. So I still think this peak is simply proton-electron transfer coupled. But as we change pH, we change the concentration of cations, and apparently the cations can interact with one of the species, presumably OH, and that leads to this apparent non-Nernstian shift. Without going into the details, we can see that this peak indeed depends on the concentration of cations. We've also done the DFT calculations to calculate where we would expect this peak to happen. We can see that when we do DFT calculations, if we adsorb a water molecule in a step site, it has the tendency to dissociate. It will dissociate into hydrogen and OH, and depending on whether the potential is negative or positive, you'll either have a hydrogen-covered step site or an OH-covered step site, but there's going to be a narrow window where, in principle, you have both. So DFT predicts that a water molecule is not stable on a platinum step. And we can calculate that peak, and we can calculate how that peak shifts with different cations, and we can see that we can get a reasonable agreement with experiments. So this is at least a reasonable explanation. So currently my understanding of this peak is that this peak is the replacement of hydrogen by OH, and the binding strength of the OH is very sensitive to the nature and concentration of the cation. And that's because both cation and OH, they both sort of compete for solvation. And that's what we see in the DFT calculations. So that's our current understanding. That's important because that basically means that what we always thought, namely that we have only hydrogen adsorption in this hydrogen region, no, we also have OH adsorption, and cations also matter. Now, just to show you a highlight from Francesca's thesis, we always, when we did the 553, which was our favorite step single crystal, because we have a high step density, we always saw some signals there in the voltammetry that we didn't fully understand. And if you do careful electrochemical STM measurements, you actually find that if you do this on 554, the terrace width is what you would expect it to be. But if you do the same experiment on 553, sometimes you got terrace widths that are, twice as large as you expect it to be, suggesting that there is step bunching. And you can go through the entire experiment here through the analysis of the surfaces and make these kind of histograms. And we clearly see that as you go to higher step density, there's a tendency for these steps to step bunch. And that's obviously important because then you change the concentration of steps, and this is presumably important for understanding catalysis, and this is also something that Francesca argues in this paper. This also made us realize that we can probably recognize this now from the voltammetry. There's often that we saw this kind of this shoulder on this sharp peak here, and now we know that if we see this shoulder that we should take that as evidence that we have step bunching. It doesn't mean that I know exactly what this shoulder means and what the charge under the shoulder means, but it does mean that we have step bunching. And that's I think was a very important result because it made us realize that if we go to too narrow terraces, that we probably do not have the nominal surface that we think we do. So here again is the polycrystalline voltammogram. You see this hydrogen region, what we classically call the hydrogen region. It's only a hydrogen region on platinum 111. On all other surfaces, it is a hydrogen OH cation region. I think that's important to realize. We still call it a hydrogen region. I still call it a hydrogen region. But on polycrystalline platinum, it's not a hydrogen region. It has more than just hydrogen. This double layer region here, I would argue, is only a real double layer region in terms of free charge, or it's ideally polarizable on platinum 111. On all other surfaces, we have adsorbates sitting there. We have hydrogen sitting there. We have OH sitting there. Their coverage change as a function of potential, but it's not a clean platinum surface. And that means that we have every charge that we measure, if we integrated the current here, that is what electrochemists call total charge. It's not just free charge, it's also the charge that we use to make these surface bonds. And then the question is, how do we separate that? Because you would still like to know then, what is the real excess charge? What is the real electric field? From that, you would have to separate the charge that is used to make the adsorbate bond from the total charge, and that's not so easy. I'll show you an example later where this can be done, because you can then play with the time scales of adsorption and charging, but that's certainly not always possible. So you probably would have to start integrating this with other techniques that would allow you to measure this free charge in a different way. The other thing that you may have noticed, I think there's many small peaks in electrochemistry always. I've totally ignored this little one here that does not have a cathodic counterpart here. I'll come back to that later, what that could be. So now we go a step back and we go back to, let's say, classic double layer theory. And so suppose now, and this probably is going to work for platinum 111, we work in this double layer window, we change the potential, we change only the free charge on the surface. And then there's a classic theory that is known as the Gouy-Chapman or Gouy-Chapman-Stern model that explains how the capacitance of this interface would change with potential. And so it can also then predict the charging current that you would expect. And basically this is a purely electrostatic model which describes the electrolyte as a dielectric continuum, and it interacts with this charged surface. It's a bit like a de Baeyehukel type model. And what it predicts is that we can see this interface between the metal and the electrolyte as a series connection of two capacitances. One would be the inner layer capacitance or Stern layer, and that basically has to do with the size of the ions. So how close can they come to the interface? So this would be the plane of closest approach of a solvated ion that does not undergo any chemistry. And then we have a part of the double layer where the screening of the charge that exists here is more diffuse. So we have a space charge layer, and that space charge layer is described by the Gouy-Chapman model. It's basically a de Baeyehukel model. And for the Gouy-Chapman model, we can calculate what this capacitance of this space charge layer or Gouy-Chapman layer would be as a function of potential, which is E here, and as a function of the bulk electrolyte concentration, which is C of B here. And the potential here is referred to with respect to a potential that we call the potential of zero charge. And that's the potential where the free charge on the surface is expected to be zero. And it remains to be seen where that potential actually is. Yeah? That is presumably a quantity that depends on the electrode material and the surface that you use. Now you can then see if we go to low electrolyte concentrations, this capacitance becomes very small and it starts to dominate. And so at low electrolyte concentrations, we expect to see only the Gouy-Chapman part of the capacitance. And that also gives us a means to determine where the potential zero charge is. That means that if we're in a potential window where we know our system behaves like this, we could go to low electrolyte concentrations. And then at the potential zero charge, there's a minimum expected for the capacitance. So the classic way in which we would determine the potential of zero charge is go to low electrolyte concentrations, measure the capacitance, and if we see a minimum, that's our potential zero charge. And this was done by David Graham in the end of the 1950s for mercury electrodes. And he basically verified that all these theories were correct for mercury. So that's now textbook material. I've always been interested, can we then use this for platinum 111? Can we use this whole theory to determine the potential zero charge of platinum 111? And of course, I wasn't the first who wanted to do that. Actually, one of the first people who wanted to do that was Tamas Paikossi, who was at the University of Ulm, where also Wolfgang Schmickler was, where I did my postdoc. This was around the same time, and actually he published this a little bit later, but he was doing these experiments when I was there as well. And he said, you know, I go to low electrolyte concentrations. I want to determine the potential zero charge of platinum 111. I expect a minimum of the capacitance, and there I have my potential zero charge. And he was trying to do all these experiments, and he failed. He could never find a minimum that would be consistent with a potential zero charge. And he wrote a paper about it with an abstract of 2 sentences. And basically, this is a paper with a negative conclusion, since with lower solute concentration, no Gouy-Chapman minimum can be found. He saw a peak in the capacitance. He also concluded that then the peak is also not related to potential zero charge. So this is a report of a failed experiment. And it's so important to publish this kind of stuff, no? Because this kept me thinking. So this should work, and it didn't work. And he really does nice experiments, and it doesn't work, and we couldn't understand why. I remember discussing this with him when I was there. Why don't we see the minimum? And I think when we came to the conclusion, probably this potential zero charge, we cannot see it because it's not in the double layer region. Suppose it's here, then we cannot measure it because we measure the capacitance of the hydrogen absorption. So we cannot see it, and we cannot separate this capacitance from the charging, and so we can never see it. And we came to the conclusion this is probably the reason, and we don't see it. But then there was a paper by the group of Juan Feliu, which basically covers a very obvious result, namely that potential zero charge should be dependent on the pH. And I'll show you why. What they found, indeed, they could measure the potential zero charge in another way. They have other methods. There's other methods that sort of approximate the potential zero charge. And you can imagine that you can use probes that can tell you how much charge is in the double layer. And if you do that measurement, then indeed you find that the potential zero charge is at 0.3 volts versus normal hydrogen in the hydrogen region. So we cannot measure this with Gouy-Chapman. But this is an electrostatic quantity. This is a pH-corrected reference scale. Electrostatics doesn't know about pH in that sense. So there's no proton-coupled electron transfer in electrostatics. And so that means that if I go from pH 0 to pH 1 or 2 or 3, the potential of zero charge should shift. Because this should be constant on the normal hydrogen scale. I'm plotting here everything on a pH-corrected reference scale. I could have also plotted this on the normal hydrogen scale, and then this whole voltammogram would have shifted, and the potential zero charge would stay where it is. Key conclusion, at pH 3, if this is really true, at pH 3, the potential zero charge should be right in the middle of the AA window. If you do the experiment at 1 millimolar per chloric acid, and of course, Thomas Paikossi did that experiment, you don't see a minimum. So I was completely, I could not figure out what was happening when I realized this, and I gave this to a postdoc. Here you can see that this is classic work from David Graham, where you can see that at 1 millimolar you get a very nice minimum, and we don't see this with platinum. So I gave this to a postdoc in my group, and I said, you know, can you do these measurements again? We must have overlooked something. And here are the data that he got. So here is platinum 111, 0.1 molar per chloric acid. You see, of course, since you have high capacitance here and high capacitance here, you'll get a minimum somewhere. You see a minimum here at 0.52, which was not far from the 0.3 that we expected. So this is probably not the potential zero charge, if Juan Filiu was right. Then you go to 1 millimolar of perchloric acid, you get this red curve. You get a minimum here, but it's not where we expect it to be. But yeah, it could be, maybe. You see something, a maximum here that Paikossi was also referring to. But then if you add electrolyte and you keep the pH constant, the minimum should stay where it is. And it shifts a little bit, and there's another peak here, but it's not where we expect it to be if Juan Filiu was correct. So I was still puzzled. This still doesn't look like a Gouy-Chapman potential zero charge. And we couldn't figure out what it was. And then it's always good if people who do the experiment are not prejudiced, because then he did an experiment. If he would have told me, I'm going to try this experiment, I would have said, don't do it. It's not worth it. But he did it anyway. He said, well, if I don't see this at pH 3, I'll just go to pH 4. I go to even lower concentrations. And that's what he did. And he got a minimum. This is exactly where you expect it to be. Remember, 0.3 on the normal hydrogen scale, pH 4, that's 4 times 60 is millivolts. So we expect that this minimum should be at 0.53, 0.54. That's not too bad. But more importantly, as we add electrolyte without changing the pH, the minimum stays where it is. The capacity just goes up, just as in the experiments of David Graham. And so we thought, okay, this is it. This is the potential zero charge, but at anomalously low electrolyte concentrations. We shouldn't see this at these low electrolyte. We should see it already at 1 millimolar, and we saw it at much lower concentrations. So that's the reason why we never will be able to see it, because nobody ever went to this crazy low electrolyte concentrations. So what is happening? Why is this then there? Now, one way to analyze this is also something that Cassina dug up from the literature. There's a way to analyze this, and that's a so-called Parsons-Zobel plot, where you plot the measured capacitance versus the capacitance that you expect according to Gouy-Chapman, and you do this as a different concentration of electrolyte. And if you do that for mercury, you see you get a nice straight line. You get a slope of 1. Beautiful. That's why this works so well. And basically, Parsons and Zobel did this to extrapolate to infinite concentration so that you can then estimate the inner layer capacitance. If you do the same plot for platinum 111, you also get a slope. It's not even clear if this is linear. I'm still not sure if this is linear, to be honest. But you see the slope is much smaller for some reason. Now, why is it much smaller? I guess this is still an open question. There's now different papers in the literature that would explain why this slope is much smaller. But one thing that it suggests is also the capacitance is much higher for a given electrolyte concentration, is much higher than you would expect it to be on the basis of Gouy-Chapman. That suggests that there is an additional interaction channel between the ions and the surface that is not taken on board in the Gouy-Chapman model. However, we also know that there is no chemisorption because we don't see any chemisorption in the voltammetry. So we basically built a very simple toy model where we added an additional interaction channel, which is sort of parallel to the Gouy-Chapman, where we have some kind of relatively weak interaction. And if we turn on that weak interaction, we can get Parsons-Sobel plots, which are quite similar to what we see experimentally, at least with slopes that are very much smaller than 1. And you can get that for interactions that are about 0.2 electron volts. So those are not chemical bonds. Those are weak interactions. I'll come to you later how I currently interpret this, but that weak interaction can in principle explain why we get higher capacitance and why we need to go to anomalously low electrolyte concentrations to see this. Importantly, I think this is still an electrostatic interaction. We see that it doesn't matter what kind of anion or cation we use. The Parsons-Sobel slope is very, very similar. So it's not specific to the ion type. So that suggests it's electrostatic in my mind. We can see that it's sensitive to the difference in size. We were probably lucky. We did this initially with sodium perchlorate, but we can see that if there's a big difference in size between the anion and the cation, we can see a shift in the minimum. And this is something that our model can in principle also explain. And combined with a very simple model for the inner Helmholtz layer that was suggested by Jun Chang, we can sort of roughly reproduce the capacitance trends that we see experimentally. That still doesn't tell us why we have this relatively weak electrostatic interaction. There's now a paper in the literature. We already suggested that maybe it's an image interaction that is weak enough. You wouldn't expect that image interaction if water has the dielectric constant that it has in the bulk, because then that image interaction would really be too weak. But if the dielectric constant near the surface is lower, then the image interaction becomes stronger. And maybe that explains why we have this. And maybe then this image interaction is different between platinum and mercury, which is maybe not so unreasonable. Still, I think this is unsolved. But in my mind, because it's weak and we see it's not sensitive to the nature of the anion, in my mind, it's effectively electrostatic. But this is, I think, still an unsolved issue. But you see how important it is in determining the potential zero charge, because we need to go to anomalously low electrolyte concentration. There's one other thing before I go to what we see when we go to step surfaces, and this is something that we got a lot of comments when we did this work, that we measured the capacitance by just doing voltammetry. And most electrochemists don't like that. No, then you just take your current, you divide by scan rate, you get the capacitance. And they say, no, you need to do impedance, you need to do AC voltammetry, you need to do the oscillation. When in principle, they're right. But if you just have a simple capacitor, it shouldn't matter. You should get exactly the same number. So we finally did the experiment and we saw actually that it does matter. And if we do the impedance, we get different numbers. But for a different reason. It turns out that what we thought was a perfect single crystal does not behave perfectly electrostatically. We saw that there is a small deviation from a perfect capacitance that is something that you would model by a constant phase element. And this constant phase element is basically if your exponent here is 1, you have a perfect capacitor. But if this deviates from 1, you have a little bit of a resistive component in your capacitance response. And we see that experimentally, that there's a slight deviation from ideality. We can do the measurements. It doesn't really matter. And in the end, the effect is relatively small. The Parsons-Sobel plot is also very similar. But what's most interesting is the potential dependence of this deviation from ideality. This is this constant phase exponent, which if everything is ideal, it's 1. And you see if we go to high electrolyte concentrations, it's sort of 0.99, which is pretty okay. But we saw that if we go to the low electrolyte concentration, there's a clear dip, and the minimum is right at the potential of zero charge. So the potential of zero charge is also the potential of minimum constant phase exponent, if this is correct. And you can even see that if you go to a pH 3 here, your minimum of constant phase exponent shifts by 60 millivolts. We cannot see the minimum in capacitance anymore at pH 3, but we can still see the minimum of the constant phase exponent. So maybe this is almost a method to determine the potential zero charge. Is that where your deviation from ideality is maximum, which surprised us a lot, that at the zero charge, you would have a maximum deviation from ideality. And we did some measurements or some simulations, because basically you can model this using, you know, COMSOL if you want, so Poisson-Nernst-Blanke simulations. And if you do this for a flat surface that is perfectly embedded without any side effects, then you actually, what you see is that you get most ideal behavior at the potential zero charge. And then as you move away from the potential zero charge, things start to become ideal, non-ideal, especially if you have low electrolyte concentrations. And that is basically due to the limited mobility of the ions. So this is what the COMSOL simulations predict, which is exactly opposite to what we see. So we came to the conclusion there must be something more. And one thing that we think could be explaining this is the way we do these experiments. So this is a single crystal. We make this hanging meniscus. And we think that this hanging meniscus, especially around the rim here, has some kind of electrowetting. So the structure of this meniscus is presumably potential dependent. And this is what we currently think is causing this deviation from ideality. So what we can explain this minimum if we think that is, so this is what is expected according to Poisson-Nernst-Blanke, and this is something that we can reproduce if we take into account the potential dependent wetting of the meniscus. This is still something that we need to check. Right now it explains what we see. We've been trying to embed the electrode in a holder, but that didn't really work so well yet. But in principle, that should lower the extent of this, but it's really difficult to make a holder that doesn't leak, and that makes things worse. But our current understanding is that this deviation from non-ideality is due to the electrowetting that changes as a function of potential. Okay, so let me go. And this is probably the final part of the talk. Let me go to what happens if we now start introducing step size. So I talked about the double layer of platinum 1-on-1, and we have this narrow region where it seems to be a real double layer, but not behaving according to Gouy-Chapman. So what happens now if we start introducing these step sites? And we already understand that at these step sites, we have dissociation of water. So there's chemistry taking place there. So it's something that electrochemists would refer to as pseudocapacitance. So you see a capacitive current, but it's not real charging, it's chemistry. So how does that then influence the double layer behavior? So this is now the double layer capacitance measured as a function of potential. And here is the one determined from the impedance spectroscopy. And you see that the trends are the same as we start increasing step density. And this is a step of 1-1-0 orientation. And we see that the capacitance minimum shifts to lower potential as we increase step density. So potential zero charge shifts, presumably, if the capacitance minimum is indeed the potential zero charge, which actually, if you think about it, remains to be seen because we do not have a homogeneous surface. We also see that the capacitance decreases with increasing step density. And why am I highlighting this? Because if we do the same, but now for the 1-0-0 step site, again, we see the capacitance minimum shifts to a lower potential, but now the capacitance increases with step density. So apparently these steps have a different effect on the double layer. And then we can compare, if we believe that this minimum is the potential zero charge, we can compare that to the work function, because in principle, there should be a one-to-one relation between the work function and the potential zero charge, if, of course, the potential zero charge is measured under conditions of pure double layer behaviors. There's no chemistry taking place. And it is known, and I guess you know that, as you increase step density, the work function of platinum goes down. And this has been measured for the different step surfaces with different step orientations. So this is the UHV, and this is what we measure experimentally. So we see the same trend electrochemically, but the slope is clearly different. So somehow there is a different effect under electrochemical conditions of these steps on the work function or a potential zero charge. And the easiest, and it's immediately when we saw this, I immediately thought this must be due to the fact that we have OH sitting in the step site, because in the potential window where we measure the potential zero charge, there is an OH sitting in the step site. And this presumably quenches the dipole due to these step sites, because the steps generate a dipole and that lowers the work function. And this is quenched by the chemistry that is happening there. And presumably this is what we see. The other interesting observation is that now we can look at these Parsons-Zobel plots, and we can see that if we do this for the 100 step density, we see that the slope remains the same. So we still see that the Parsons-Zobel slope is much smaller than what we would expect, but there's actually it doesn't change as a function of step density. And in my mind, that suggests that presumably there's an adsorbate sitting there, but the coverage of that adsorbate does not change with potential, hence does not generate any pseudo-capacitance. It's just sitting there, and it doesn't change with potential, and so it doesn't have a contribution to the capacitance or the differential capacitance that we measure. And that's why there's no step adsorption capacitance. However, if we do the same experiment for 100, we see that the Parsons-Zobel slope changes with step density, suggesting, and this is known, that as you increase pseudo-capacitance, the Parsons-Zobel slope will go down, suggesting that here we do have a sizable step adsorption capacitance. And that would suggest that the OH coverage in the 100 step, in the region where we do this measurement, actually changes as a function of potential. That generates a pseudo-capacitance, and that also explains why the capacitance go up as we increase the step density. That also explains why we see the Parsons-Zobel slope go down. We did some ab initio MD and DFT calculations to see if we could calculate this potential of zero charge. There's a way to calculate this. And one thing that we see here you see the calculated work function. And then as we start increasing, we put OH in the step site. This is for 0.2 monolayer. This is for 0.4 monolayer. Indeed, you start seeing that the slope changes. But in these ab initio molecular dynamics simulations, it's very, very tricky, because it's very difficult to get very good statistics. So we did the same with just doing DFT calculations, putting an OH on the step site, no water, just calculate the work function. And indeed, we see that the OH on the step site basically quenches the dipole of the step site. And we get much less of this Smoluchowski effect, where we have a dipole due to the step site, and it's just quenched by the presence of OH. And we think that that in principle could explain why we get this much lower slope that we see experimentally. So in my mind now, this is another piece of evidence that we have adsorbates sitting in the step site where we measure the potential zero charge. We have adsorbates sitting in the step site, and they quench the dipole, the electrostatic dipole of the step site. This has a few consequences for polycrystalline platinum surfaces. So the double layer window on polycrystalline platinum, I would argue only on the 111 facets you have free surface charge. All other facets you have pseudocapacitive charge. And so the electric field also then is likely the highest at the 111 facets, because the charge that we calculate from the voltammetry is mainly pseudocapacitive charging, and it's not actually free charging on all the other facets. And so in the double layer window, we can see that the 100 facets actually dominate, and this is also why we see that the 100 step sites lead to an increase in capacitance for the single crystals. We see that typically in the double layer window, the 100 facets, they dominate, they have the highest pseudocapacitance, and so they basically dominate the charging current in the double layer window. Here we see the different facet distributions of different polycrystalline materials, and you see the ones that have the highest contribution of 100, they have the highest capacitance. So that current in the double layer window is dominated by the 100 facets. So that does bring us back to the question, is there a way to separate this? If we measure this, can we somehow separate the pseudo-capacitance from the free charge capacitance? There is a way to do this, but unfortunately only in alkaline media. In acidic media, the proton transfer to form adsorbed hydrogen is a very fast reaction. We can try to do experiments at very high frequencies, but it's too fast and we cannot separate. But if we do the same experiment in alkaline media, then there's actually a barrier associated with making adsorbed hydrogen. And then if we go to high enough frequencies, we can basically separate the pseudocapacitance from the charging capacitance. And that basically has to do with the fact that we now have this charge transfer resistance, which is absent in acidic media, but it's there in alkaline media. And now we can separately determine the double layer capacitance at a given hydrogen coverage from the adsorption capacitance. And that makes it possible to determine the free charge capacitance of a hydrogen covered surface, but only in alkaline media. And if you remember, in alkaline media, if I increase the pH, the potential zero charge shifted positive, positive. So actually the potential zero charge in alkaline media is very, very positive. And this forms a relatively negative potential. So we automatically have to work at very negatively charged surfaces to measure this kind of capacitance. And so we cannot find, easily at least, the potential of zero charge that would correspond to such a hydrogen covered platinum surface. We can do the measurements. We typically see that these capacitances are much smaller than what we see in acidic media. Originally we thought maybe these capacitances are much smaller because the surface is hydrogen covered, becomes hydrophobic, maybe that lowers the capacitance. But right now, probably the most likely explanation, or certainly one that we cannot exclude, is that the potential of zero charge is somewhere here. And so the surface is very negatively charged, and then automatically capacitances tend to become much smaller. So we think this is mainly a field effect and maybe not so much a hydrogen effect. I think I will skip the last, I will skip maybe one thing to say about this little peak here, just for you to, because I said I would talk about this. We see this little peak also on single crystals, but only on single crystals which have 100 sites. And what we see is that if we take here a platinum 110 surface and we keep it at a very negative potential for a while, so we generate a lot of hydrogen and then we go positive, we see this peak. And then we come back, it's gone. So apparently this peak is a site that we form on the surface when we adsorb a lot of hydrogen on the surface, suggesting that the surface restructures under the influence of hydrogen, and it only happens with 100 sites. It does not happen with 110 sites. No, it doesn't happen with 100 sites. And we did some DFT calculations. This is from Ian McCrum. That here you have a straight step edge, and here you have a step edge that is sort of faceted, and then you see you make these 100 features. And the straight step edge in the absence of hydrogen is more stable. But as you start adsorbing hydrogen on the step edge, you see the step edge at some point becomes more stable. And if the surface is fully covered with hydrogen, actually the faceted step edge is more stable than the straight step edge. And obviously this requires quite a bit of reorganization of the surface. So it has a relatively high barrier that you can also calculate. And that's presumably why this process is so irreversible. And so we don't see it if we go negative, and we need to go very positive. We facet the step edge, and then as we go positive, it slowly repairs, and we can see a separate peak. And so we think under the influence of hydrogen, these step edges, they change structure. And actually there's some evidence that if we go even more negative, also the terraces, they can change structure under the influence of hydrogen. And that is something that you can see here. So this is again platinum 111 in sodium perchlorate, acidic media, but now at extremely negative potentials. And then we see that we start making these holes, these triangles in the surface. And we think this is due to the formation of these pits that also generate these 100 sites in the surface. So we start making pits in the surface, and we think this is due to the interaction of the hydrogen with the platinum. Now we probably make some multi-layer hydrogen, a hydride that selectively etches out these type of pits from the surface. We did DFT calculations to see that this is indeed expected to happen at these negative potentials. 2 or 3 monolayers of hydrogen is in principle stable. You should expect this to form. These are hydrides that we form. We can calculate the corresponding Xane spectra of these hydrides, and we managed to actually do the experiments. I have to say this on polycrystalline surfaces where we see the formation of these hydrides, or at least they give us these spectra that look very much similar to what we calculate experimentally, suggesting that we form a hydride and not so much a platinide as an intermediate for this, what we call cathodic corrosion. Suggesting at these very negative potentials, we make a hydride on the surface that in the presence of cations actually can corrode the surface very, very quickly. Okay, that brings me to my conclusions. I showed you that there's a free charge, double layer on platinum 111, but step sites are always covered with hydrogen or OH. And so it's very difficult to associate any free charge with them. The double layer of platinum 111 does not seem to follow the classic Gouy-Chapman model. There seems to be an additional interaction channel that we can argue what that interaction channel exactly is, but it's weak. It seems to be effectively electrostatic, but it increases the capacitance much beyond what we expect on the basis of Gouy-Chapman. Step platinum has a much more complex double layer. We see again evidence for OH formation on these steps, and that changes how the potential zero charge changes with step density from what we see from work function measurements in UHV. And then if you go to higher concentrations of hydrogen, we see that the surface actually changes structure, and this goes for both steps as well as for terraces. These are the sponsors of the work and all the people involved, and I would like to thank you for your attention.